Hey everybody, welcome to the Kanthal Heating Systems webinar on heating elements for glass tempering. We're going to get started here in a few minutes, but I just want to make sure that everybody can hear me and let you know that we have a conversation window as well as a Q&A pane. So please let me know if you can see and hear us. And also let us know where you're coming from. We are sitting in the US, but we have people joining from all over, so I'm curious to hear where you guys are joining. Like I said, we'll get started here in just a few minutes, so thank you for your patience. All right, so it is 11 o'clock here Eastern Standard Time, and we will go ahead and get started. Just a few things before we get started here. We will be sharing a copy of this this video recording for all those to view back. So if you have any troubles or need to hop out before the end, feel free to take a view of our recording. So with that, I will pass it over to Art Maslow. He's our technical marketing manager for Kanthal, and he will be taking you through a little bit more about heating elements for glass tempering, some selection, and talk a little bit about our offerings. So with that, I will pass it over to you, Art.
All right, thank you, Jason, and thank you everyone for attending. I guess it's a good morning, afternoon, and good evening to everyone for joining us today. So welcome, as Jason said, to the Kanthal webinar on electric heating elements for the glass tempering industry. I'm Art Maslow of Kanthal, but just real quick before we get started, I just wanted to remind everyone to stay safe. Safety and a healthy environment are priorities here at Kanthal. So Kanthal has an objective for zero harm to people and the environment we work in. So these are some of our safety priorities. So I know it's during the global pandemic that we have now, it's probably even more important for everyone to work in a safe environment. So with that, we'll get started. Just quickly, details on what we'll be talking about today. I'll be covering on the webinar just a brief introduction of myself and Kanthal for anyone that's not familiar with our company. We'll focus primarily on heating element selection, covering alloy grades, alloy shapes, element styles, and the reasons for selecting one over another. And then we'll answer any questions at the end of the presentation. And as Jason indicated earlier, we'll send a follow-up details to everyone later on. So first, briefly about myself. I'm the sales engineering manager for North America, working at Kanthal with both of our Kanthal materials, so it's our alloys and our heating systems, which are heating elements. I've worked at Kanthal for the past 18 plus years in various engineering and sales related roles, and I'm currently working out of our office in North America, located in Amherst, New York, which is a suburb of Buffalo. So Welcome again to everyone joining us. And then a quick introduction of Kanthal. We're a global heating materials and systems company. We have offices and manufacturing facilities throughout the world. We have approximately 2,000 employees, over 5,000 customers. So we have a presence in some form or fashion everywhere you might be located. And our main headquarters are in Hallstahammar, Sweden. So, as part of the introduction, I just wanted to kind of discuss briefly about the glass tempering application and have some quick general background details on the manufacturing of glass, just to kind of set the stage for introduction of the heating element discussion. So just a general overview on the basic glass production process. It's fairly straightforward. It's the raw materials are going to go through a melt, and then a float, and then forming, and then annealing, cutting, or a tempering process. That's just kind of a general overview. And a float is a process done at relatively high temperature, 1100 C or 2000 Fahrenheit, and it's a formation of plate or flat glass. Essentially, it's a molten glass flowing on a tin bath, and then it's slowly cooled, goes under a controlled cooling process to get the right shape and thickness of glass. Then more of a forming process is annealing glass. It's the process it's done at various temperatures, and it's done to remove any residual stresses from the forming process within a shaped product, for example, like a glass bottle. And then another finishing process would be what we consider tempering glass. It's done at 650 degrees centigrade or 1200 Fahrenheit. And it's really done to increase the strength of the glass and to add a safety factor to the glass. Now, glass annealing, as I said earlier, is a post-forming heat treatment of the glass done in an annealing layer, and that's heating with either gas or electric. An annealing layer establishes a homogeneous temperature profile within the formed product. It's to alleviate any residual stress in the material. Formed products like glass bottles in the picture you can see here, and they have a variable temperature profile after the process before they're annealed due to the variable shape and thickness of the glass. And then the last kind of intro slide, just a little bit more detail on glass tempering. Essentially, tempering is a process that increases the strength of the glass by a factor of 4. And it's a heat treat process conducted in a higher temperature furnace, about 650 centigrade or 1200 Fahrenheit. It goes through the furnace, and then it undergoes a rapid cooling. That's cooling on both sides of the glass as it passes through an air cooling chamber. And this process locks the outer surface in compression and the core of the glass in tension. So essentially, when the glass breaks, it's going to crumble into shards that can be picked up with your hands. A lot safer than if you broke a beer bottle that's very sharp, jagged, and could easily cut you. So it's important to note that products that come out of glass tempering are typically a simple flat shape, and that ensures a uniform temperature profile, and they cannot be cut or drilled after they've been tempered. And then some products that are made for the glass tempering application. You might have architectural glass, like windows, doors, tables, stairs, railings, etc. Some sports arena applications, like boards for hockey rinks or backboards for basketball hoops. A lot of automotive windshields and windows, display cases, office partitions. A lot of appliances will use tempered glass. I know a lot of people do a lot of home remodeling lately in bathrooms. You might have their shower doors, refrigerator doors or trays, any cookware, diving masks. So there's a lot of different products that are tempered. So essentially that's the general background on glass tempering. And now we'll get into details about electric heating elements. But first I want to cover some background just to set the stage. These are basic details as it's related to electric resistance heating. Resistance heating utilizes conductive materials, so conductive alloys, and it converts the flow of electricity within the alloy into heat energy. And that is based on the resistive qualities of the material. So different alloys have different resistivity properties. And that's all based on Ohm's law. So the simple voltage is the amperage or current times the resistance, or you get a resulting power, which is the voltage times the current. So just as a quick reminder, electrical resistance is a material's opposition to the flow of electricity. So that's measured in ohms, so the resistance. And like friction, water flowing through a pipe or anything else, it generates waste, which is, in this case, is in the form of heat energy. And that's the result we want to get out of the material, is the resulting heat. And resistance heating is used in everything, like your toaster at your home or an industrial furnace at a steel mill. And it's just the scale of the heating can vary greatly from one application to the next. Now we'll get into a more interesting topic probably for everyone, and why they're here is about heating element selection and design. It breaks down into a few different identification factors. We have alloy grade. Typically it would be a nickel chrome alloy or an iron chrome aluminum alloy. So that's kind of the two main alloy grades used for electric industrial heating. And then you have alloy shape. For instance, you might have wire, which is round, or strip, which is a flattened form. You might have then you have a style of heating elements. You might have coils, rod overbends, bundle rods. There's a lot of different types of heating elements and styles. And then you'll want to be aware of the heating element specifications. These are the dimensions, essentially the output of the heating element into the system. And then we'll cover quickly just why Kanthal. Why are we discussing heating elements selection and design? With heating element designs, it's important to consider the element life, as element failures will impact your production cycle of the glass. So typical element life is measured in years for this application, perhaps on average of 2 to 3, but it could be less or more, and it's depending on the application. Now, I have just included here some details in pictures of some common element failures. Here at Kanthal, we can assist on conducting investigations on causes of element failures and can make recommendations based on that investigation. So you might have overheating, corrosion. This is green rot. It's specific with nickel chrome alloys. Might have sulfur attack, so it's maybe something from the process or your atmosphere. Again, uneven pitch of coiled elements, so it might be from elements sticking to the refractories. You can get scratches on the coil during manufacturing or during installation, so it exposes some of the base material. And then you could also have some poor element design, so we can look at that, where maybe you have a bundle rod heater where the discs are too far apart and the straight legs of the element are sagging, the hairpins. Or it just could be the way the terminals are connected to the element, or the way the element is installed or utilized. Perhaps it's underpowered for the application. So the first detail when selecting heating element design is, as I said earlier, are details related to the resistive alloys. Resistive alloys are alloys that allow for the flow of electricity and are capable of operating at high temperature. That's a key aspect. There's plenty of alloys that allow for a flow of electricity but cannot operate at a high temperature. You need the combined effect of the two in order to have a good alloy for installation into an industrial furnace. And the high temperature resistive alloys essentially fall into two categories, or two groups. You have nickel chrome, or nigrothal as we call it here at Kanthal, or iron chrome aluminum, or Kanthal alloys. And there are various grades within each of those groups, different grades of nickel chrome and different grades of iron chrome aluminum. And then you also have alloy selection. It's based on the furnace or the application requirements. So you have to consider quite a few things, such as the temperature of the furnace, and that's how it's going to relate to the oxidation and strength of the heating element, the atmosphere of the furnace or the application, and that affects the operation, the presence of the element, or if there are any presence of chemicals or gases you might have to consider. Then the operating cycle of the furnace. So it's related to how the furnace is run. So whether it's just like an on-off, either the furnace is running or it's not. You might have intermittent use where you might be cycling it occasionally or not or whatnot. And then you have continuous use where it's always on. You also have to consider mechanical properties. So, so related to the furnace geometry, the orientation of the elements, might be the configuration of the elements. And then the power requirement, the wattage of the furnace, to maintain the desired throughput or to maintain the temperature in the furnace. And then just there are two basic details showing the differences between the two groups of alloys, the nickel chromes and the iron chrome aluminums. So performance mostly revolves on the protective oxide layer formed on the heating alloy. So nickel chrome, it forms chrome oxide, and iron chrome aluminum forms an alumina oxide. And the oxide formation and thickness differs between the two alloy groups. So on the left, I just showed details here on the chemical content of the various grades of iron chrome aluminum alloys and various grades of nickel chrome alloys. And then the graphs here on the right just show some comparative life between perhaps an element that's identical but made with the different alloys. And then the oxide performance of the different types of alloys. These didn't have the graph labeled here, but the APM and APMT, that's more of an iron chrome aluminum alloy, and then the iron nickel chrome is more of a nickel chrome alloy in its performance of oxide and spallation. And then we have here some pictures showing the performance of the oxide, and then some basic strength of the materials, and comparisons. The more the oxide that spalls off the alloy, it's oxide thickness and spallation. There's a difference between an iron chrome aluminum alloy and nickel chrome. What happens with a material that has a thicker oxide that tends to spall off more, which is like a nickel chrome, you're going to consume more of the base material. So in this case, iron chrome aluminum has an aluminum oxide or alumina oxide. So you're going to spall off aluminum, and you're going to consume aluminum in the base material. And then with a nickel chrome, it's a chromium oxide, so you're going to consume chrome. And also there are details on differences between the creep strength of the materials. So you might get, depending on the alloy that's used, you might get bunching of a coiled heating element. This bunching could result in overheating and shorter life. So and this is just to kind of show the differences between, different grades of iron chrome aluminum. You might get less bunching or more bunching depending on what grade of alloy you're selecting. The next selection criteria concerns the alloy shape, the shape of the raw material that the element is made from. And there are three essential basic types. You have round wire, which is just traditional round wire. It's just as it says. And then you have two different flattened type wires. So you have ribbon, and sometimes these get mixed up, ribbon and strip. Ribbon is basically you start with a round wire and then you flatten it. So the edges of ribbon are rounded, so it's a safer material to handle. And then you have strip, which starts as a coiled strip, so basically a flat rectangular piece of material that could then be rolled and flattened to get a specific thickness. So it's just important to note that the edges are square and sharp, so they're not rounded like a ribbon material. And it's just, I wanted to point these different wire forms out because typically different styles of heating elements will perform better using one specific alloy shape or another. So, for example, traditionally round wire is used with a coiled heating element. It's not always the case, but it's typically the case. And next we have different element styles. So we have typically these might be used anywhere from 100 degrees centigrade up to 1300 degrees centigrade, or 212 degrees Fahrenheit to 2372 degrees Fahrenheit. So this is our metallic element style temperature range. You might have round elements. These are probably the most common used in the glass tempering application. You could have ROB type elements using strip material or using wire material. And we also manufacture, or you might use, bundle rod type heating elements or RT heating elements, and that could be with either a nickel chrome alloy or an iron chrome aluminum. That's true with all of these different types of heating elements. Then we also have seen in heating elements that are used in the glass industry for air heating cassettes or plug rack heaters. I wanted to include some graphs to demonstrate there are differences for recommendations when designing heating elements based on the style of heating element and how it's used within a furnace. So this is all part of the heating element selection process. The two graphs here just show some comparative information on a coiled element and its resulting watt loading. So it's basically its power output, and comparing a coiled element that's freely radiating, so it's supported on a ceramic tube that spans the furnace chamber, and then another different type of coil heating element that's installed within grooves that's contained within the insulation walls in a furnace. So we consider that like a semi-embedded heating element. And you can see in the graphs that there's different watt loading recommendations depending on what style or alloy that's used. So it's a nickel chrome or an iron chrome aluminum, and the different ways that the elements are installed. Another example I have here is for ROB or meander type heating elements. So ROB stands for rod over bend, so it's essentially just a sine wave or a loop of material. And the loading recommended loading for the design can vary depending on if it's using round wire or strip material. And again, differences between nickel chrome and iron chrome aluminum. And also you'll note on here that it also shows differences on how the elements are controlled. So it all has to do with the control system, whether it's on-off, so it's cycling through a SCR that might be burst fired or zero cross type, or also type of control where it's using more of a softer phase angle fired SCR. So, some details, additional details to help with elements specifications. We use a lot of design questionnaires and element drawing templates. So essentially it's you want to gather all the furnace particular details and parameters in operation of the furnace. And then we have a lot of details about coiled elements, since this is kind of probably the most common type of element used in glass tempering. It's not the only type, but it's the most common type. Typically, as I said earlier, these elements are suspended by a ceramic, typically mullite tubes. And there could be various different styles. It has to do with the single leg, multi-shank elements. You might have single and multi-hot zone elements, so you might vary the pitch of the coil intentionally to adjust where the heat is concentrated along the length of the element. And you also might have elements located in the roof or the floor of the furnace. Another type or style of element is a strip element, and these would be strip ROB type elements. You might have a folded strip element where it's laying flat. Basically it's material folded on itself to form an ROB, rod over bend type element, or you might have a double strip style element where the element is resting on the strip edge. So it's not laying flat like a folded flat element. But these are two different styles of strip ROB elements. Another type of element, or an element assembly in this case, would be glass cassettes. So it's a series of elements that are pre-assembled onto a structural tray or frame and then inserted into the furnace from the sidewall. So instead of trying to insert one element, you essentially be inserting perhaps a whole circuit within an element. So it's a series of elements. And then the last style that I'll cover is a porcupine element or a plug rack heater. These are more heaters used for air heating. So you'll have a flow of air passing over the heating element and transferring the heat from the heating element to the airflow. So, and then a porcupine element is a three-dimensional coiled element that's supported on a ceramic tube. This it's kind of like a shape of a spirograph that's stretched out over a ceramic tube, and that provides a large surface area for airflow and heat transfer from the element to the airstream. Some tools used for verifying element specifications. And we use a lot of physical tools in our daily work in designing heating elements and determining existing heating elements and everything else. Essentially, it's to gather information. So we have element specification questionnaires and drawing templates. I have some examples on the next slide. And then just some basic element tools used for, to get the dimensions and specifications of an element, like taking pictures, using a tape measure. It's important to note, I have this list here just to point out that you typically might want to use a magnet to help identify if it's a nickel chrome alloy, which is not magnetic, or an iron chrome aluminum alloy, which would be magnetic. Typically, when designing elements, you want to use calipers. So not just, you don't want to measure round wire diameter dimensions using a tape measure, because that's not precise. You want to use calipers, because you can get a lot more precise dimension on gauge sizes of wire or strip material thicknesses. And you might want to use a low ohm meter. That's to measure the resistance of an element when it's disconnected from the power supply. Here's just some general templates we use for getting all the specifications and details and parameters of a heating element, and ensuring when we design a heating element, all the parameters are included. And then I just have two more quick slides, and then we'll get on to the question and answer period. So just quickly, why Kanthal? So, and this question comes up, Kanthal is, we manufacture the heating alloy wire, and we have the technical expertise with the full range of heating alloy grades and heating element styles and designs. So we can help you select the proper alloy, select the proper alloy shape or configuration, and the element style to best suit the application. And lastly, we also can help with any issues that you might have. If you might have as I said earlier, you might have element failure analysis that you need help with. You might have an application where you're looking for faster throughput, higher temperatures, more power out of the system. You might be looking at longer element life, so essentially element performance. And we also can look at element limitations to kind of overcome some limitations. As I showed earlier in the graphs, different styles of elements and the way they're installed have different limitations. So that essentially wraps up the presentation. I just have a slide. I just kind of want to open it up for any questions that you might have.
Excellent. Well, thank you, Art, for walking us through that. We do have a few questions which came in through the Q&A panel. While we get started answering these questions, I'll ask you, if you have any existing questions, please feel free to reach out in the pane. There's about a 15-second lag with this broadcast, so we want to make sure we get to all your questions before we end. So the first question is asking about if we have molybdenum alloys.
We don't. We do manufacture molybdenum disilicide, but that's a ceramic-based material used for heating elements. If the question revolves around molybdenum wire alloys, Kanthal does not manufacture molybdenum wire, so nor tungsten or graphite. Typically, we're not involved with heating elements like this in vacuum type applications.
Okay, moving to the next question. It says, you mentioned that annealed glass is needed for manufacturing of tempered glass. Do you also make elements for those furnaces, meaning the annealed glass furnaces?
Yes, we do. Annealed glass furnaces use either gas or electric, and for electric heating elements, typically the annealing leader uses like some type of air heating cassette. So typically we call that a plug rack heater. So it's kind of the last couple slides I showed some pictures of air heating cassettes, or the plug rack heaters. It's coiled elements or porcupine heating elements on ceramic tubes contained in some type of metal housing or frame that's dropped into a furnace. So the short answer is yes, we do.
Okay, excellent. And then we have our last question here from John, asking what type of wire is best for glass tempering? Alloy, round, flat? Really,
that comes down to what shape the element is. So most common that we see in the industry would be coiled metallic elements. So, and in this case, a lot of the elements that we're designing would be the iron chrome aluminum, like it could be Kanthal AF or A1 or APM. So, and typically when someone asks what's the best, I'm thinking what provides the longest life, so the best performance. So it's a great question. Thank you.
Thanks, Art. Okay, the next question here is asking about if we still manufacture Kanthal D and LT grades for wire and strip, and if they come into play for this manufacturing process.
We still do manufacture Kanthal D. That's an iron chrome aluminum alloy that's lower temperatures, and we typically use that for our terminal configuration for all the different types of heating elements, whether it's a coil element, a bundle rod type element, or an ROB. A lot of times they're using the Kanthal D alloy for terminals, and that's just for heating element design. Now, there are other applications like appliance heaters that might be operating at a lower temperature. They could use the Kanthal D alloy or other grades of Kanthal alloys that we manufacture. So we could send additional heating element alloy details if needed.
Excellent, and that actually relates to the next question, asking if I need help with my furnace, how should I reach out?
Oh, that's a great question. As I pointed out earlier, we have a sales office or manufacturing facilities throughout the world. So typically there is a Kanthal representative or a Kanthal salesperson that handles a specific area, whether it's a country, a state within a country. So, and going to the Kanthal website, we have a complete listing of how to reach out to your salesperson. On the website, we also have a chat bot. So just going to the website, usually the chat bot comes up. You can, and then someone is always manning the chat bot. I know a few engineers that work in the U.S. We're manning the chat bot during our working hours, but that's manned all the time. So we can quickly get someone in contact with you for help.
Excellent. Another question that came in asking Should we use strip wound or wire wound elements, and mentioning specifically glassed in furnace?
It really depends on what element style is there. The furnace builder will design an element based on the configuration of the furnace. So the furnace builder will communicate with the customer on how they want their glass manufacturing process to work, and they'll then look at where do they want heating elements installed and how much power is needed. And there's a lot of requirements that the furnace builder will communicate with the customer, and they'll use, so there's really no set answer for this. They'll use any type of heating element, and it's really application specific. So a lot of furnace builders will use all different types of heating elements depending on the process they're designing for a specific customer. So.
Excellent. And the last question here, which I can take, is asking about if we can get a copy of the template used for measuring and quoting the element, similar to what's shown in the slides. And so we will compile material and also answers to the questions that you all had today, and that will go out in an email within the week along with the recording, so that you have some access to the resources that we have today. In addition, we also have published a glass tempering web page, which you can download our metallic heating elements handbook, and there's a lot of great information which Art used to pull out, used in the slides today. Looks like we have a couple more questions actually come in here. This is regarding maintenance. The question is, are there any maintenance suggestions needed to be done on the heating element to extend the lifetime? And similarly, we had a question which earlier asked about the lifetime. If the lifetime is 2 to 3 years, is this with constant use in production?
Typically, a lot of the alloys, whether it's nickel chrome or iron chrome aluminum, can be used in intermittent operation. It's typically not always a continuous operation. So it's more of what happens in an element design. Element life kind of comes down to the oxide spallation. So it really relates to how hard the element is being run. So it's power output. So any type of maintenance that can be done, there are times if there is some type of protective atmosphere used in a furnace, and the customer is able to purge the furnace during a maintenance cycle, or perhaps during a holiday time when their furnace is off, and they're going to kind of pre-oxidize or re-oxidize anything else in a furnace, whether it's the insulation or any other structural supports or rollers. Running the furnace in air occasionally will help, because it'll re-oxidize, it'll reform that protective oxide layer on an element. So typically, a lot of maintenance really comes down to when a furnace is shut off, just doing a physical, getting kind of eyes on the elements and kind of take a look to see, properly replacing failed elements. Because if you leave failed elements in operation, it could result in existing elements that have not failed being pushed harder to maintain that furnace temperature. So you could be running the elements that have not failed at a higher temperature than what they're designed for. So that could lead to shorter element life. So it's just kind of general maintenance, inspections, and replacing elements that have failed, and making sure elements aren't sticking to the furnace. So it's kind of like just some general ideas.
Excellent. I think that wraps up pretty much it, all the questions we have. Like we said, we will pass along this information in an email along with the recording. Likewise, if you'd like to get in contact with us, as Art mentioned, feel free to reach out to us. We have the live chat, and yeah, we'd be more than happy to get you in contact with somebody from our technical marketing team. So with that, thank you everybody for joining today. We will have similar webinars in the future, and you can follow them on Kanthal's website. But thank you for joining today. Thank you, Art, for your time, and we hope you have a good rest of the day. All right, take care. Thanks.
Thank you, everyone. Take care.